now let's look at some realistic cells that people make using these multiple junctions. Okay, so remember this problem we did in one of the long questions we had in problem set 2, where you guys optimize the efficiency of we gave you two materials and said find out what is the maximum efficiency of this cell using a Shockley-Coizel kind of formulation, right? And all of you drew these beautiful looking contour plots in your homework, right? So now this was, if you thought this was complex enough, right? Now for that problem we had given you that assume complete absorption of light. Usually you have a finite absorption coefficient, and you also have to take into account the thickness of these cells as well, right? So you have to optimize it taking the finite amount of thicknesses of these top and bottom cells. And then you might have to do it if you do it for AM 1.5 spectrum, and versus if you do it for, let's say, AM0 spectrum, which is what you see if these cells are used in space, is that you'll see different values because these spectrums are different, so you'll get a different optimum point, right? So if you thought this was difficult for 2 cells, now try doing it for 3 cells, right? So this is what people who design these cells have to do on a routine basis. So they have to design these efficiency, or instead of drawing these contours, now they have to draw these 3-dimensional contours where you have the top band gap material over here, and then you have the intermediate band gap over here, and then you have the lowest band gap over here. And you get these contours which will give you what is the maximum efficiency you can get if these things are series connected, just like the way you did it in your homework problem. Now it would have been much easier if you guys would have gone with me and said, let's put an extra terminal, but since you didn't, we have to deal with this. So now I have to essentially optimize for all these 3 band gaps, and shown here are some of these optimum cells. So you usually get this top band gap. If you look at the optima of this lies somewhere around 1.8 to 1.9 if it's a 3-junction cell. The intermediate cell lies between between usually 1.2 and 1.4, and this lowest band gap cell, the band gap of this comes to be around it's actually best if it's around 0.8 or 0.9, but in reality with the semiconductors we have, this is usually around 0.67, which is the band gap of germanium. So each of these points on this curve, it represents what is the efficiency you can get with that cell, and then what is the band gap corresponding to that. And these are some of the champion cells. So, these are some of the best material combinations that people have realized, and the band gap of those materials. Okay. So now this was fine, we did this theoretical exercise, but now comes the material scientist and he says, okay, you have given me the 3 band gaps, how the heck I'm supposed to find these 3 band gaps and grow them on top of each other, right? So he will come and he'll stare at this plot for at least a few days, okay, and he'll try to find out where are these lattice combinations, where are these these 3 materials which I can make them appear in this curve where they have 3 different band gaps which I need, and they also have the same lattice constant. So since you guys chose this solution which has 2 terminals, now I have to find these materials which are lattice matched on top of each other, so I can grow them on top of each other. And so now this is a nightmare, right? So theoretically I might be getting some value, but I'm constrained by my hands are tied by the law of nature, and I'm constrained to use only those systems which are lattice matched to each other. So the most common system which is used is this system which is grown on germanium. So this is my bottom cell, and this is lattice matched with this gallium arsenide, which is an intermediate band gap material. And then this is finally on the top for the highest band gap photons, we have gallium phosphide over here, and we have indium phosphide over here. So in between what is used is typically a indium gallium phosphide with approximately same percentage of both indium and gallium, and this forms your top cell. Okay. Now there have been people who have tried to think different and do something differently. So people have tried to go to this system, which is indium phosphide, and now this would be lattice matched to, let's say, indium gallium arsenide over here. The speaker who will come on Wednesday, he uses a very it's not just different, it's actually out of the box. So they use this material which has gallium nitride or indium nitride, which has a lattice constant which is not even on this figure, so it's over somewhere over here, and they use a combination of this with indium arsenide, so that gives them a very large latitude, or that gives them a lot of headroom to play around with these materials combinations. So that maybe you can ask him about it and get all the secrets from him on Wednesday. But so the main challenge over here is to realize these systems, which are realize these three band gaps, which are lattice matched to each other. Okay. So this is what is the most commonplace three junction cell. So it uses first of all, the thing you should notice is that it has all of these multi-junction cells. They have layers and layers and layers. They're just like onions, or have layers and layers and layers of materials. So you have these three cells over here. The bottom cell is germanium, which has a band gap of 0.67. Then the intermediate cell is gallium arsenide, or gallium arsenide with a little bit of indium added to it, and it has a band gap of approximately 1.4. And then you have this top cell, which is my blue cell, and it has a band gap of 1.85 or 1.89, right? And now you also see this anti-reflection coating over here, and this is, as you can see, this is using a bilayer coating over here, which is a combination of dioxide and aluminum oxide. Okay, so you see all these features that we talked about, right? And now you also have these window layers, you have these back surface field layers, and these are also made up of materials which have the same lattice constant as well, right? So you see how many layers there are, and you can feel the sympathy or empathize with the person who is responsible for growing these and making these cells. Okay. So to show the suffering of that person, I'm showing the different ways you can grow these cells. So the most common way which is used is to start with a lattice match system. So the system I showed you, that is, start with a germanium cell, which is my red cell, and then have my intermediate cell, and then my highest band gap cell. But they have to be lattice matched. But my hands would be tied, or I would be very restricted if these systems have to be lattice matched with each other, right? So there's not much material system I can play with. So the other option is to use a system which has slight lattice mismatch, right? So I start with maybe still germanium, but I'll grow another material system, let's say indium gallium arsenide, which has a slightly larger lattice constant as compared to germanium. So the problem with that is that you get defects, okay? And you get defects while you're growing these material systems. So you get stacking faults, you get these other point defects, and all kind of imperfection in your lattice. And these love to recombine, or they love to act as recombination centers, right? And further, if you get these defects here, they'll propagate throughout the cell, okay? So not only will they damage this cell and the intermediate cell, but they'll also cause recombination in this top cell, okay? And that's again a bad thing. So what some people, one approach that has become popular recently is to start with a higher band gap material. So instead of starting the growth on a lower band gap material, you start maybe the growth on this indium gallium phosphide, and then you grow these lower materials on top of it. And then finally, if these defects propagate, they will propagate throughout this cell. But what I'll do then is essentially flip this cell, and now I'll shine light from the top, right? So I have taken the cell, I have flipped the growth, So if these defects propagate, they'll affect my bottom cell, but my top cell, which is facing the light, is still defect free because I started from that, right? So this is what is called the inverted metamorphic growth, or instead of starting from the lower bandgap material and growing on top, I'll start with a top bandgap material and grow on top of it, and then I'll flip the cell and use it on the other side. Okay. And the other thing which people always talk about, which has been a pipe dream, is to realize these on low cost substrates such as silicon. So ideally, you would want so that you have these two cells, and you could just wafer bond them to a silicon solar cell. So we spent the last few weeks talking about silicon solar cell. So why not take this other cell and just combine the two, and voila, I have a 3-junction cell. But again, the problem over there is bonding between these two cells. That leaves a lot of unpassivated surface state, which cause a lot of reformulation. So nothing is easy over here. So you can see that if I use more and more junction, I can realize higher and higher efficiency. So if I use one junction at a concentration of 500x, I can realize the efficiency of 40%. If I go even higher, I realize even higher. But you see that this comes at a cost of increasing complexity. So if I use 2 junctions, maybe I'll have 4 times the complexity. If I use 3 junctions, I'll have 8 times the complexity, right? So usually people, usually their appetite for complexity dies after using 3 or 4 cells. So 4 is the maximum you typically use. Even in commercially, what is available is mostly 3, but in labs people do make 4 junction cell. Another thing you see is that you're getting this diminishing increase. So if you're increasing the number of cells, it's not that this curve is rising like this. It's more, you're getting diminishing return with each increasing junction. So 3 or 4 is where people stop. Okay. And now to give you some more feel of this complexity. So now think you made this cell for you optimized it. You maybe spent years in your lab optimizing it for this AM 1.5 spectrum, right? Now suddenly NASA comes to you and say, can I use this for space? Okay, so what will you say? Go use it for space. Will it work equally well? Will it give you higher efficiency? If I optimize the cell for, let's say, use in California, I optimize my band gaps so that I can use it here on a solar farm here, would it work equally well if I send it to space? Why? Yeah, so essentially, the space, it has atmosphere, it shaves off a lot of this spectrum which is located in the ultraviolet and in the blue part of the spectrum, right? So suddenly this cell, especially this top cell which had optimized for absorbing this blue light, it now becomes saturated because now there are too much of these blue photons available. There are too many of these high energy photons available. So what people do is essentially they'll have to reduce the thickness of this top cell such that it current matches with these bottom cells, because now suddenly the spectrum is different, right? So the current density which I had matched for these 3 layers now is no longer matched, right? So now think of, if I had 4 cells, I'll have to optimize it again for, optimize the thickness of 4 of them again, right? And even the spectrum changes between here versus if I'm using it in Phoenix versus if I'm using in, say, Africa, or versus if I'm using in India. Each of them has a slightly different air mass, has a slightly different tilt, has a different spectrum, right? So if I use these, let's say if I use 3 or 4 junction, I have to optimize the thickness and I have to optimize the band gap for every time I change my spectrum. So you see the problem over here that, that's why it's important that NREL at least collects these spectrum and at least makes them available for different parts of the world, so different parts of US at least, so people know how to design the multi-junction cells, right? There was, I remember there was this some construction company in Dubai. They wanted these concentrated cells, and people didn't know what the spectrum was there, right? Nobody has like measured it and collected data, years of data on it. And now if I want to design this multi-junction cell, this knowledge of this spectrum is like critically important, right? Okay, so actually, let me end with this. Another thing which is really important for these cells is concentrators. So these cells work best if you use them with a concentrator, just because your open circuit voltage, it increases with the concentration. So your VOC, essentially, if you it's given by this equation where it depends upon your short circuit current. So higher is your short circuit current, or higher is your JSC, higher is your VOC. So the higher concentration of sunlight you use, the higher open circuit voltage you get. And with the caveat being that you don't heat up the cell. So if you use again too high of a concentration, then again your VOC and your efficiency, they start to fall, because you're heating up or you're increasing the temperature of the cell. So usually the optimum concentration that people use is around 500 to 1000 x. Okay, so let me show you just one video, and then we will come back and discuss it. I'll show you more videos and we'll discuss these in the next class. Okay, so okay. So this is one such concentration system. It achieves a concentration of, I think, 500x. Okay. So this is the cell. This is the size of the cell. Okay, because you're concentrating your cell so much, the cell is only a very small size. Okay. And let me show you another one, and then we'll compare the two.
Okay, so what we have here is a concentrated photovoltaic system that converts sunlight into electrical output and at the same time into thermal output. And the system uses a big mirror, like you have there, to concentrate sun 1000-fold onto a semiconductor chip. It's a triple junction photovoltaic chip that converts then the sun into electricity. And because of the high concentration, the power density is very high, and we have to cool the chip. Instead of just throwing away the wasted heat, we are using the heat for processes like desalination and absorption cooling. And the system works with a multi-chip concentrator, which is located in the focus of the mirror. And there we have the semiconductor chip, and we also have the cooler with the tubes that are driven by the test station here. So we have a chiller that transfers the heat away, and we have the electrical installations that measure the efficiency of the photovoltaic conversions. So we need
this
to be careful with
he has to wear glasses to go near.
The mirror concentrates the solar radiation 1000-fold on the spot there. And the spot has to be on an active cooled surface, and if there is no active cooled surface but just an aluminium beam, it will melt the beam in seconds. There is a current trend to replace nuclear energy in Europe with alternative energies, and sun is the...
So you saw that person has to wear these very dark black shades to go near it, because if you concentrate light by 500x, if you put your hand on if you look at it directly, you'll go blind, right? So, and the other thing he was saying that since it produces a lot of heat, he's using this water, and many a times these things are used in conjunction with producing hot water, which is usually used for chilling. These guys were trying to use it so that water is usually used for air conditioning, and these guys were trying to use it for desalination, where you use it to convert salt water into fresh water, right? So that's another use of this. So this is what, this is a concentrated system. So it concentrated light into the cell. This is usually, it can concentrate up to 1000x before the cell starts to get hot and blow up, right? The other one which you saw, which was this block, which that square kind of a system which I showed in the first video. So that was a Fresnel lens, right? So does everybody know about Fresnel lens? So instead of using one big lens, you essentially split that lens into these many small things over here, and then you use that to concentrate this light into that small cell. So that person was holding that very small chip, and that was the size of the cell. So it was